Alex, I think you can go ahead and dive in. Other people will trickle in. We'll just give them, and they can catch up. Anything they miss will be on the recording.
Hey everybody, my name is Alex Merced. I'm a developer advocate with Dremio, which you see over here, and I'm going to be talking today about Iceberg, which you see on my shirt. Okay, it's a very exciting topic, definitely a topic I'm very passionate about. It's been an exciting year for Apache Iceberg in just the world of open table formats in general. So we're going to dive deep into that, and we'll take an architectural look under the covers. Again, you can follow me on Twitter over there at AM Data Lakehouse, always creating content around data lakehouses, open table formats, any kind of open source technology regarding the data lake and the data lakehouse. Now, in today's agenda, what I want to do is talk about what is a table format. So first off is like, I've been hearing all this hype about Apache Iceberg, but everyone's saying it's a cool table format, but what is a table format? Why do we need a new one? Like, what was so wrong with what came before that we needed something new? How does an Apache Iceberg table work? Like, what is its architecture? What is the structure that enables all these cool features that we're hearing all this sort of hype about? And actually, what happens when I run a query? So when we run a read query on Apache Iceberg table, like what is the actual like step-by-step process that's kind of going on under the hood for a write, etc. And what are the resulting benefits? Like basically, once we take a look at all this structure, all this architecture, like what does this all enable? And basically, what's in it for me? Okay, so that'll sort of be our story for today. So let's begin. We're going to talk about what is a table format. Okay, we all know what a table is, right? We've all used a database or a data warehouse. At the end of the day, like we generally store data in a place, generally in a unit called a table, and we can run queries on that table. And we generally take that for granted because that database, that data warehouse abstracts so many different steps in the process of like how is the data stored, how is the data accessed, all this stuff. We just run our queries and it's just like magic. But the problem is, as you get bigger and bigger data, petabytes and petabytes of data, you're going to generally kind of want to store it somewhere that can kind of facilitate that. And that's generally like the data lake. Okay. And generally in the data lake, whether you're talking about like in a Hadoop cluster or you're talking about object storage like on Amazon, Azure, Google Cloud, you're talking about a lots of different files. So you're no longer looking at a table, but you're looking at maybe like thousands of Parquet files that make up petabytes and petabytes of data. Okay. So the idea is that we want to find a way to take a look at those sea of Parquet files, sea of ORC files, that sea of Avro files, and be able to say, okay, hey, this group of files here represents one singular data set, one singular table. Okay. I mean, you could kind of do that back in the days of like MapReduce, but in like MapReduce, you'd have to sit there and say like identify on every MapReduce script and say, okay, these are the files that are I'm querying this time around. And the problem with that is if you're defining your data sets on every process, you end up with a possibility of like inconsistent data. Okay, so we want like a place where there's a standard definition of what is a table on our data lake. And we want to even go beyond that so we can really enable this whole data lake house paradigm where the data lake can act as like a data warehouse. Okay, so what happened was the idea is like, how can we treat all the files as a table? And the original approach was done through Hive. Okay, so the Apache Hive project came out. Its main intent was to make it easier to use MapReduce in those old Hadoop days by saying, okay, instead of you having to write these Java MapReduce scripts, how about you just write SQL? And Hive would then translate all that SQL into a MapReduce script. But SQL kind of really depends on this whole idea of a table. So you need to have a definition of a table. So the way Hive handled defining what a table was is that it would use a directory-based approach. It would say, okay, hey, this is a folder. Any files in this folder is a table. Okay, so when you say, select all from X, anything in the X directory is what's inside of X. Okay, so whatever is inside the folder is the table, and it was simple as that. Okay, and then any subfolders would be partitions and so forth. And that worked. Okay, that definitely solved the problem. There was a way that when you wrote those queries in Hive, that it was able to know what table you were talking about because it would just look for that folder with the right name and look at the files inside the folder. Okay, and that became the de facto standard. So when you wanted to run a read query, so particularly like reading the data on your data lake, Hive offered a pretty good option. And and still to this day is what a lot of, if not the standard. Okay, and again, this offered lots of benefits. It works with basically every engine. Like pretty much any tool you have for working with the data lake works with tables that follow that Hive format. Because you're working with tables, you're able to do certain things that we take for granted in like traditional databases and data warehouses, like things like partitioning. So we're able to partition our data, which allows us to query the data more efficiently. Because I can be like, I only want to query the data for this month, and then it would only access the folder for that month, and I'm scanning a lot less data. It was file format agnostic. Again, whether it was a Parquet file, an ORC file, an Avro file, other types of files, if it was in the folder, it was part of the table. Okay, so that works. Okay, because like each partition was its own folder, you could atomically update a whole partition, because essentially what you're doing is you're just rewriting that partition with all your updates, and then it just kind of swaps it out. So you could safely rewrite a whole partition and update a partition. And again, it provided that single central answer, that consistent answer to what is the table. Okay, through 12 different analysts query the same table, they are querying the same set of data because it's the same files in that same folder. And there's a lot to be said for that. Okay, but there was still a lot of problems. If you want to make small updates, like you want to update one row, okay, you're essentially updating the whole partition to update that one row. That's very inefficient. And again, that inefficiency costs money because you're running a much more intense compute, and those compute costs add up. Okay. No way to change multiple partitions safely. So you could change a partition safely, but it was much harder when you started working and wanted to make updates across multiple partitions, especially if you're having like concurrent writes. So again, having multiple jobs, concurrent jobs, you start introducing a lot of complications of what you could do safely on the data lake if you wanted to do like mutations and things like that. And then essentially since you're working with a folder, essentially the way it would figure out what's inside the table is that it would go inside the folder, list all the files in the folder, and it would just iterate through like a list of files. So it have to so even if it's like Parquet files, it's still got to open up the file. So you got to there's an open operation. Then you got to read the file. There's a read operation, and then when you're done reading that file, there's a close operation. Then you move on to the next file. So this whole iterating from one file to the next was again something that took a lot of time. So essentially, like conceptually, we can reduce the time of these queries if we read less files and just read less data. Okay, that's always generally like the idea. You can always throw more compute power at it, but more compute power is more expensive. Or you could just do less stuff, and then that's cheaper, and you get to that same better speed place. Okay, and that's generally where we're going to be kind of going with Iceberg. It's really going to facilitate that way of being able to optimize by working smarter, not harder. Okay, and one other issue you had with a Hive format is the way it handled partitioning. So imagine this scenario. I have a timestamp column, and it measures like the timestamp of a sale. Now, what I want to do is partition the table by month. Okay, I can't partition it based on that timestamp column because it's going to partition for each like unique value. That's not going to work. So what I'd have to do is create another column derived from that timestamp column that measures a month. It gives me like a number like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. And then partition based on that. Okay. And the only purpose of that column was for partitioning. The problem is if I'm the data consumer and I wasn't informed that there's this extra column, this month column that the partitioning is based on, even if I query and say, hey, give me all the data from this timestamp to this timestamp, I'm still going to end up scanning the whole table because I didn't include the partition column in my query. And so you can have these accidental full table scans. So that's what we mean by you really need to know like how the table was set up. So not only did the data engineer need to know how they engineered the table, but also the consumers need to understand how the table was engineered to get the full benefit of. And generally like the less the end user has to know about the engineering, the better engineered the product is. So that's kind of what we're going to try to find a way where we can design a format where I can just use it and not have to think about it. It just optimizes when it needs to optimize. And with Hive tables, you would generally have to run these analyze queries to generate statistics. So it's not like the statistics were being generated incrementally. You would have to run these like queries that would have to go read the whole table, generate these statistics, and they were done periodically. And so your statistics were never as fresh as you'd like them to be. So we had all these hosts of problems. Again, much better than what came before Hive, but again, there was definitely a need, and Netflix saw that need. So and Netflix in particular was like, okay, we have a lot of goals. We would like to. This is not working for us. This is we have petabytes of data. It's taking us way too long to query this data. So we need to kind of create a new format that is going to, provide us those correctness, that consistency of the data, that definition of the table. It's going to allow us to plan queries a lot faster, and it's going to have to allow users to just be able to query the table. If if their query can be optimized, it should just be optimized. They should have to be worried about having to like add additional clauses to their queries. You should be able to evolve these tables. I should be able to change the schema. I should be able to change how the table is partitioned. I should be able to change a lot of the details of the table without having to rewrite the table, because that would oftentimes be the case sometimes with Hive. You want to change the schema in certain ways. If you wanted to change partitioning, you would just have to literally rewrite the whole table. So we want the table to be able to evolve and do all of these things at petabyte scale. Okay, so they took a different approach. So the original creators of Iceberg coming out of Netflix basically said, okay, well, how can we do this differently? And the big fundamental insight here is that instead of looking at the table as a bunch of files in a folder, instead you take a look at them as a canonical list. So it doesn't matter what folder the files are individually in, there's going to be a master list of the files that make up the table, separate from the directory. Okay? And if you're on that list, you're part of the table. If you're not on that list, you're not part of the table. So basically, the folder is not what determines what's in the table, it's the list of files. And as we'll see, that list of files is going to contain all sorts of metadata that's going to allow us to more efficiently access those files. So what is Iceberg at the end of the day? Well, like, what is a table format at the end of the day, and what it isn't? A table format like Iceberg at the end of the day is a specification. The idea is to have a standard playbook for how the data is stored and how metadata around that data is tracked. Okay, because the metadata is really the special sauce. It's a thing that engines are going to use, whether you're talking about Hive, Spark, Flink, Dremio, they're going to use to look at that table and determine, okay, this is how I'm going to query that table. This is my plan of attack. So it's a specification. It's basically a standard for how certain metadata files are going to look like, containing data that engines can use to determine, okay, what files am I going to scan, where am I going to scan them, all that kind of stuff. And then on top of it, it's a set of APIs, so a bunch of libraries that make it easier for engines to adopt and build in that Iceberg functionality into them. Okay, so there's a bunch of Java APIs, Python APIs, bunch of built-in Spark libraries and Flink libraries that just make it easier to sort of like adopt and use Iceberg. But Iceberg is not, okay, it is not a storage engine. Okay, you store it wherever you want. You could store it on a Hadoop cluster. You could store it on object storage. Okay, Apache Iceberg actually has special features for scaling on object storage. It's not an execution engine. Okay, Iceberg itself doesn't execute queries. Okay, so you might have an Iceberg table, but you will still need a query engine like a Spark, a Flink, a Dremio, a Hive, something that can then actually have a query and process it to read that data. Okay, and it's not a service. It's not Iceberg. You don't have to have an Iceberg server. It's not this continuous running service that you have to then go, provision a separate compute cluster or something like to run. It's just a standard format in which the metadata is written. So let's start taking a look at that standard. Like, how does that all come together? Okay. So we're gonna start taking a look at the pieces of that specification, the pieces of that standard that any engine that talks to Iceberg tables expects. Okay. So we're going to go an overview of these components. The first component, and really the heart, in my opinion, is the catalog. Okay. So what is the role of the catalog here? In the case of Iceberg, the catalog acts as like the phone book. Okay, I always just like liken it to the phone book. So when I think about like, if I go back to like the 90s and 80s, okay, I mean, sometimes you still use the phone book nowadays, or you go to yellowpages.com. But once upon a time, you had that big, thick book. And you'd be like, I want to know what Bob Jones' phone number was. And you would flip through the book and you'd find Bob Jones and there was his number. And then you could call Bob Jones. That's what the catalog is. Okay, you run a query saying, hey, I'm looking for table one. I'm going to go to the catalog. It's going to have a list of the tables that are in that catalog. And then I'll be able to say, hey, where is table one? And literally the only thing the catalog will have is a pointer to where the metadata exists for that table. Okay, that's pretty much the extent of what the catalog is going to hold. But the catalog is generally going to be some sort of thing that can have like asset guarantees, provide a lock. So this could be something like a Hive Metastore. There's actually an open source project called Project Nessie that's specifically created to be sort of play that role for Iceberg, that offers like Git-like functionality and a lot of other cool stuff. I'll mention that again later. There is a HDFS implementation for a catalog, which pretty much works like a Hive in the sense where basically it's the folder that determines the table. But that doesn't necessarily have the same guarantees as using these other things like Hive Metastore, AWS Glue, Nessie, a JDBC compliant database, DynamoDB. Any of these things can be used as your catalog, and those things would provide a lock and really can provide you those asset guarantees. Cool. But essentially, what happens is that if I'm an engine and I'm running a query, the first thing I'm going to do is I'm going to go to the catalog, whatever catalog you've connected to, and say, hey, where's the table? And that's generally going to point to where that metadata file. Okay, so that's going to be sort of like our first rung of metadata. And that's a nice thing about the way Iceberg does metadata. It's not like just one type of metadata file. So it's not like it's actually like a tree of metadata. And there's different tiers that play different roles. Okay, so the top layer is called the metadata file. And the metadata file, the way to think about that, this is the table why this defines the table. Like it's the global metadata. So this is going to tell the engine, like, this is the table. What is its current schema and what are its previous schemas? What is its current partition scheme and its previous partition schemes? What is the current snapshot and previous snapshots? Essentially all the data about the table. Okay, and then basically I can always use this to refer back to as far as like how the table is defined. Now, if I'm querying the data, I'm going to look at the data at a particular point in time, aka a snapshot. So if I'm looking over here, looking at the metadata, I'm going to see, hey, look, here's the current snapshot. And it's going to give me a snapshot ID. And then it's going to look for that snapshot ID in this array of snapshots. And then each snapshot has a file called a manifest list. That's the next layer of metadata. So we have the metadata file that defines the table. We're going to have a manifest list that defines a snapshot. So it's going to go, okay, hey, this is a snapshot I'm looking to query. So it's going to then go to the manifest list. Okay. And now we're on the next layer of the metadata. Now with the manifest list is not a list of files. Okay. They did you one better. Instead, what they are is a list of groups of files. Okay. And the beauty of this is that basically each manifest, which will be the next like layer, is the actual list of files. And then what the manifest list does, it lists all the individual manifests that make up that snapshot. And the cool thing is I can then go begin pruning from here. So if I'm the engine, I can start looking through each manifest list or each manifest listed in the manifest list and take a look at its partition specification and see, hey, does this particular file important for my particular query? Because I may be scanning only one partition and I can see, okay, hey, this is not in the partition I'm scanning. So I don't need to look at that file. So I don't have to like get rid of files one by one. I can get rid of big chunks of files at this point. So it starts going through all these different like entries of manifests and starts saying, okay, I don't need to look at this one. I need to look at this one. I need to look at this one. I don't need to look at this one. And then it takes the remaining manifest. So any manifest that didn't get pruned at this point, we then go scan those. Okay. So that'll be the third layer. And each manifest represents a group of files. And it's generally like a group of files that were added to generally a particular partition. There's some variations on that, but the idea is it's a list of individual files. And then once we get to this layer, it has in data we're going to have metadata not only on where the file exists, but it's actually going to have min-max values for each column in that file. So for example, even though I may have partitioned it based on month, if I was also to say, hey, I want to query data for anyone who's like over the age of 25, it'll be able to take a look and say like, hey, this file, of all the records in this file, it only has ages between 17 and 23. Okay, I don't need that file, so let's not scan that one. So what it's doing, it's going to start again pruning and saying, okay, this file I need to look at, this file I don't need to look at, this file I don't need to look at. And again, that comes back to how do we speed up queries? By doing less work. So we're identifying really what are the things we really do need to scan to actually get the job done. And that's how we're speeding up the query. So after going through this whole process, by going through this whole tree, you go through this whole planning process, but at the end you end up with a very efficient plan where you're only scanning the narrowest subset of data that you really need to scan to get this particular query executed. Okay, and we'll show you some benchmarks later or some example use cases later to kind of see how drastically it can increase the speed. Okay, and then after that, then it will go scan the data files. And again, depending on the engine, like the Parquet files, it'll use like the Parquet headers to further refine the process and all that. Okay, but it then goes to that process of actually like scanning the actual data files, but only the data files have really necessitated scanning. Okay, so that's essentially like how it works. Now that we've seen sort of what are these layers, the catalog, the metadata file, the manifest list, the manifest, let's kind of see a few examples of that in action. Okay, so let's do this first query, which is just a query of us creating a table. So it's just a standard, create table. Here's like the schema of the table. Now, again, this is presupposing that you're writing the query in Spark. So the actual, like if you're writing this query in like Flink or Dremio or any other engine, some of the syntax may slide very, very differently. But like, for example, like this using Iceberg clause, that's basically telling Spark like, oh, okay, when you write this table, do it using Iceberg. Okay, but essentially what's happening is you're creating the table, you're specifying the query, you're saying, hey, use Iceberg, and then partition by. Now notice this is actually really cool. When you do partition by, now notice how we did this instead of our order TS. So Iceberg, when it comes to partitioning, allows you to specify a transform on your partitioning. So instead of just saying, hey, partition based on this column, you're saying partition based on the transform value of this column. So instead of me having to create some whole separate column, okay, that then I have to remember to query later on, I can just say, hey, you know what? I am partitioned based on the order timestamp field, but by hour. So essentially when it breaks up all the folders, it's going to break them up by hour. But anytime anyone filters based on the order timestamp column, even though it's just a timestamp column, it's going to try to take advantage of that partitioning. So the end user doesn't have to know that it's partitioned by hour or by day or whatnot. It just needs to know, hey, I want to look at records between this timestamp and this timestamp, and that partitioning will be taken advantage of. That's a feature called hidden partitioning in Apache Iceberg. It's pretty neat. Okay. Oh, let me go back. Okay. Let's do exit full screen for a second. Let me go back to that example. There we go. Okay. So what's going to happen is that when we run this query, essentially what's going to do, it always works backwards, okay, in the sense that if I'm writing, I need to write the metadata file first, okay? So I'm going to write this metadata file because I'm defining a table. I don't have to write any manifest because there's no files, there's no data yet in the table. And if there's no manifest, there's no need for a manifest list. There's no need for a snapshot because there's no data to snapshot. But I do need a definition of the table, and that's the metadata file. So I'll write the metadata file, and then we're going to go back to the catalog and say, catalog, we're going to put an entry and say, hey, whenever someone looks for table one, go look for this metadata, point them to this metadata file. And then here you can kind of see like what the potential like file layout would look like. So as far as like what it would write in your S3 or your Hadoop cluster, it would look like this. It would be like it would still look very similar to Hive in the sense where there's a folder for that table, but it's not required. That's like the big difference. Like it can write it this way, and generally it defaults to that setup, but you can vary from that, which is especially important for like things like object storage, where having everything in the same directory, having the same prefix could cause throttling. Because Iceberg breaks from that sort of Hive directory dependency, you avoid those issues, which is really nice. Okay, so we have this table. Now let's insert some values into that table. Okay, so I insert some values. And what's going to happen is we're going to write a data file with the new data. But then we need to track, hey, what data files have been added to the table. So we create a manifest file, which lists the individual files. Well, that manifest file needs to be part of a snapshot. So then we write a snapshot, okay, that details, hey, which manifests are part of the snapshot. And then we need to create a new metadata file. Nothing ever gets edited, okay? Everything's immutable. So we always create something new. We never modify the old. That's why you're able to consistently query old snapshots and never have to worry about, hey, like, did the old snapshot change? Because those files never change. Instead, we write a whole new metadata file, and the new metadata file has the information for the new snapshot and the old snapshot. Okay, and now we go update the catalog and say, hey, catalog, going forward, point to this metadata file. And that's going to help any queries, because any queries coming in going forward, the minute that's committed, are going to get directed to that new metadata file. Okay, and that's how we kind of prevent this whole collision between writers and readers. Because if there's a writer writing a new snapshot, well, any reads aren't going to be affected by it because they're always reading what the catalog says is the current metadata file. So that they're never going to refer to some partially written metadata file that's currently being written. So there's never like a collision, never an issue between concurrent reads and writes. Okay. So now in this case, we're going to do an upsert. So we're going to merge some data into here. So in this case, we do merge into, so we're saying, hey, we got this table here. We have some staging data. So we're going to select that staging data and call it S. And then we're going to say, hey, wherever the original table and the staging table match up on ID, okay, if they match, I want you to update the record. And if they don't match, then I need to insert that record. So it's going to, basically that query is going to run. The engine's going to figure out, hey, what do I need to write? Like based on now that I've read all the files and done my whole query process, okay, what needs to be written? It's going to write any data files that need to be written. And again, then write up the manifests that need to track those files. Write up a new snapshot tracking those manifests. And it will reuse previous, like again, throughout this whole process, if it can reuse data files from previous snapshots or reuse manifests from previous snapshots, it will. Okay, so it's not always writing everything from scratch. So you get that nice level of reuse there, which also optimizes on storage costs. And then we write a manifest list for a new snapshot here. And then again, a new metadata file that lists the current snapshot and the previous snapshots. Okay, and then again, we go update the catalog and say, hey, catalog, go point to the newest metadata file. So in that case, the catalog is always pointing to the updated state of the table. And then again, since that metadata file has the list of snapshots, I can then instruct if I want to look at previous snapshots in my queries, which we should have an example of. So now let's actually read the data. So now I just want to read all the data. So before we were writing, now when I read, it's much more straightforward. I just say, hey, go to the catalog, say, hey, I'm looking for this table. It says, yep, we got this table. The metadata file is right over here. Okay, well, I didn't specify a snapshot, so we're going to assume that I want to look at the current snapshot. So I'm going to look at the newest snapshot, which points me to this manifest list. In this case, I just select all, so there's no pruning. So it's just going to take all the manifest lists. It's going to scan all the files listed in that manifest file, and I'm going to get my results. Okay, and then that would be sort of like the read path, the read process. Okay. Now here, we're doing a query where we're filtering based on date. Okay, so even though we're filtering based on a particular date, okay, it is still based on that order TS column. So even though I'm not specifying like an hour or a month or whatnot, and I'm specifying a particular date, it's still going to take advantage of that hour partitioning. It's just going to find all the hours that are in that day. So in that case, I'm still taking advantage of the partitioning without having to worry about like adding any additional clauses. So what it'll do is it'll again go to the catalog, say, okay, where's the table? Go to the metadata file, go to the new snapshot, go to the manifest list. But at the manifest list level, what it's going to start doing is just taking a look at, hey, what partition value, because we know that we're querying that partition column because we mentioned that ORTS is what we're partitioning by. So it'll go to each one, say, hey, what's the partition value on this one? Does it match up with this query? And if not, don't scan it. And if it does, scan it. And then, we'll do some further pruning at the individual file level, at the manifest file level. And then we scan only the files that actually match that query. So then we're only scanning like one file instead of all 3 files that currently exist in the directory. Okay, so it's basically using this metadata tree to identify, again, that narrowest scope of files that it needs to scan. Okay. Now here's an example of like time travel. So the idea of like querying previous timestamps. Okay, so select all from DB, and then here we use this as of keyword. So again, that'd be like in Spark. Again, all this is assuming Spark, which again, the difference between different engines is very minimal, but just to make that clear, as of, and then here's a timestamp. So then what's going to do is go to the catalog, say, hey, where's the table? Gets to the metadata file, and then it's going to go to the newest snapshot and be like, okay, this snapshot, the timestamp on this snapshot is not as of that timestamp. So that's not the snapshot I want. So then it goes to the next snapshot. It's like, okay, is that one it? Ah, that's it. So then, so it's going to say, hey, this is the snapshot that I really want to scan. And this snapshot points to this manifest list. So then it's going to construct the table based on that snapshot's data, and then grab the manifest files that are related to that snapshot, and then scan the right data files based on that. Okay, so essentially you have that data structure allows you to kind of rebuild whatever version of the table you need. And again, throughout that process, again, whenever you can reuse a previous data file, whenever you can reuse a previous manifest, it does. So you can really like get maximum reuse out of these component pieces because you're breaking it up so much. And then also you enable some other benefits in the sense where you're not just tracking changes, but you are tracking like the actual list. Okay. Now, just to show you an example of sort of like the benefit of this, like again, where this started, Netflix. Netflix was like, hey, we need something better. So let's see the effect that this had on Netflix. So Atlas is a system over there at Netflix that collected a bunch of telemetry data. Okay, and just to kind of give you an idea of the amount of data generated by the system, in 1 month of data, it would generate 2.7 million files in 2,688 partitions. Okay. Problem was, in the old Hive way of doing things, it could not process more than a few days of data. So it made it really hard to kind of like generate data that you would need for different queries, like this example query here. So what they did, let's see what happens when you, well, I don't want to spoil stuff. Nope, there we go. Okay. Now, when you query the table with Hive, okay, so again, the idea here is you are using a Hive directory-based table, but you are accelerating the query partially using Parquet filters. So again, so in that case, it's going to go through Parquet. You might be using like Bloom filters in Parquet. You might be using like taking a look at the metadata inside like the headers and footers to kind of like reduce and say, hey, don't scan this row group, don't scan this row group. That's all fine and good. But when it came to how many splits that would have to be scanned, because again, you're still pretty much going through that whole directory, it's 400,000 splits per day of data, not combined, not total, but for each day that was being scanned, that's 400,000 splits. And to keep that as straightforward as possible, the more splits, the more stuff being scanned. Okay. And the more stuff being scanned, the longer that's going to take, the more expensive that query is going to be, because that means more compute running for a longer period of time. Okay. And if you want it to run for less time, this means you're going to need more powerful compute, which is still more expensive. Okay. So in this example, they're just running the explain query. So they're not even actually running the query. They're just running the planning of the query. So just to plan the query, it took 9.6 minutes. Okay, 9.6 minutes just to plan how they're going to scan the files. Now, if we introduce Iceberg, okay, just by using that metadata tree, and this is with only partition filtering, so that min and max filtering using the individual files for each column at the manifest level, not doing that, just using the partitioning at the manifest list level, you were able to narrow down those splits to a total of 15,218 splits. Okay, so you're scanning a much narrower world of stuff. Okay, and that's combined. So the planning of that query only took 10 seconds. Okay, so that's a big drop just in the planning, 9.6 minutes to 10 seconds. And the actual execution of the query took 13 minutes. Okay, so between planning and execution just took, just a little bit longer than it took just to plan the query with Hive. Okay, so you can start seeing like the difference. And the thing is that it's not using everything Iceberg has available to it. Again, there's also min-max filtering. That's when we get to that individual file level, and we're saying based on the individual values in the different columns, can we filter out more files? When we introduce min-max filtering, we narrowed it down to 412 splits. Okay, so that universe of what we're scanning is getting smaller and smaller and smaller. Now the scanning did take, the planning took a little longer, 25 seconds, but because you're doing all that extra planning, you saved a whole lot of time on scanning. Okay, so the whole entire query only took 42 seconds because you were able to filter out so many files, adding that min-max filtering, that the world you had to scan was so small that you got it done really quick. And again, not only is now you're performing quicker, but it's also cheaper because you're not having to pay for as powerful compute or paying for as long compute. Okay, because you're getting that query done because you're reading less files. So you're saving money and saving time. You can't ask for more than that, right? So that's essentially like the fundamental sort of like, yay, Iceberg. Okay, but Iceberg has so many other really cool features that it brings with it. Okay, you can make those smaller updates really easily because instead of having to update a whole partition, again, using that tree of metadata, if you want to update one record, Iceberg can identify the one file that needs to be updated. Okay, and you only update that one file, not the whole partition. Okay, so basically those small, more granular updates are much less expensive to do. Okay, you have snapshot isolation. Okay, so basically, again, because you have the catalog, and the catalog can act as a lock, depending on which catalog you're using. And also, again, because a read is always just going to go to the newest snapshot, and a currently written snapshot is not committed, you'll never have, I'll never read a snapshot that's in the middle of being written. And basically, if two writers were to come at the same time, what's going to happen is that when the first writer finishes, they're going to commit their snapshot. And then when the second committer comes in, they're going to double check their sequence number, and they're going to notice that, hey, my number in the chain of metadata files has been taken already. So I have to go rewrite it again. I have to go back and reread, retool. So you're never going to have this situation where like two committers write at the same time and you end up having this kind of collision of unsafe writes. So you can write concurrently safe. Multiple writers can be safe. Readers and writers can be safe. Multiple readers can be safe. It's all safe. You get the faster planning and execution, as we saw through that metadata tree. Okay, you have reliable metrics because in all that metadata, you're tracking all this data throughout that metadata that can be used to construct metrics. So your metrics are always live because they're always based on the most recent write. You don't have to run a separate query; they're there. Okay, and then that's only expanding as they make further updates to Iceberg. They're just expanding the level of metrics that can be tracked there. Like they just introduced this thing called the Puffin format, which is going to give a much more another way to kind of store a sort of a binary blob with stats that can be used, and that's just going to continue to expand. Okay. Time travel. So you'll be able to travel to previous snapshots worth of data. Okay. And that kind of speaks for itself. But just like all table formats, because all table formats have time travel, when you expire snapshots, you can't time travel to anything you've expired. So there are limits to that depending on what your regulatory needs are, because sometimes you need to delete data beyond a certain point. So you may have to expire snapshots. And in that case, you won't be able to time travel back to that. But usually you get a pretty nice flexibility there. And which also gives you the ability to roll back changes, because you can, let's say you make a mistake and you run a query that you didn't mean to run, you can roll back to a previous snapshot. So you get that flexibility, the ability to fix mistakes. Table evolution. You can update the schema. Generally, all table formats, you can update the schema, add a table. Add a column, rename a column, change the columns type. What makes Iceberg extra special though is that it's the only one where you can update the partitioning without having to rewrite the table. So you could go from like partitioning based on year and then say, you know what, we're generating a lot more data a lot quicker. So maybe we should be partitioning by month going forward. and then you can just switch it, and then going forward, it'll partition the data by month. Okay, and basically it just keeps working. Because again, it tracks all those current and previous schemas, current and previous partition schemes, and can plan the queries based on sort of how the data was written at the time. All engines can see changes immediately. Okay, so like I remember just a couple of days ago, I was just doing an example um, in a recent video I posted on LinkedIn, where basically I was writing to an Iceberg catalog, specifically using Project Nessie, um, writing to it via Spark. And then what I did is in a separate window, I had Dremio open, and I just like literally refreshed the window, and then all my changes were immediately visible. Like there's no lag between the two. So basically, you can have multiple users working on those tables from multiple tools. So you could be ingesting streaming data via Flink, and then maybe doing some L work from Spark, running some ad hoc queries on Dremio, and then all of these tools are all looking at the data consistently, which is super cool. Asset transactions, again, you have all that safety, and again, the whole architecture enables those asset guarantees. Also, you have some really good flexible features when it comes to optimizing table. Okay, so you have the ability to optimize how you update the table. So again, like updating, like if you're going to be doing frequent like row level updates, like deletes and updates, then you have the ability to switch between either a copy on write table or a merge on read table. So instead of rewriting every data file every time you make an update, you can create these what's called a delete file that only tracks the rows that you've updated, and it reduces the amount of work you do on the write quite a bit. Then it also now has the ability to incorporate Parquet Bloom filters. They have Z order compaction, so you have these compaction procedures built into Iceberg. And so not only can you take all your small files and build them into bigger files to improve performance, but you can also in that procedure sort the data. So you can cluster the data when you do the compaction. And you can just sort it based on one table. You can do Z order clustering, whatever best fits the kind of query patterns of your table. I just released an article, I think Monday, on this specific topic of the different compaction strategies and when would you use one versus the other. And again, metrics collection, because it's collecting data every time you write. But not only do you get that in Apache Iceberg, but again, I mentioned this is other open source project called Project Nessie. And it's basically what it does. It is like a project that's designed to be the catalog. So again, you can use things like Hive, AWS Glue, a JDBC database, or you could use Postgres technically as a catalog for an Iceberg catalog. They were never built for that though. Nessie was specifically built for that, and because of that, it allows you to gives you some extra nice benefits like Git-like semantics. So where this really becomes nice is being able to isolate changes to your data. So because you basically every time you make a change to any table in your catalog, it's a commit, and that means you can roll back 2 commits, and then 2, you can make branches. So for example, if I have to update 5 tables, and instead of updating them one by one, and then basically what happens, people query the data and they're querying like partially, they're only querying the data when I've only updated 3 out of the 5 tables. I could create a branch, update all 5 tables, and then merge the branch, and then the changes to all 5 tables go live simultaneously. So that way the table, it's the old data versus the new data, nothing in between. So that way it's you can create those sort of multi-table transactions using Project Nessie. It's super, super cool. And there's a lot of other really cool sort of access level features and all the other cool stuff that'll be coming to that project in their roadmap. But yeah, like that's basically the story with Apache Iceberg. There's plenty of resources. You can head over to the Apache Iceberg website, iceberg.apache.org. Okay. Me and the team over there at Dremio, we write a lot of articles. I'm on the tech advocacy team, and our job is to sit there and basically do the legwork to make sure that everyone understands what these open source technologies do and what they are capable of. And you can read our content over there at dremio.com/subsurface. The Apache Iceberg specifically are right there. You can go to there's a getting started blog at Apache Iceberg. Also, about a couple weeks ago, I put out this Apache Iceberg 101 course. So it's a bunch of videos where I walk through some of the stuff we covered today and then some, getting really granular about how Apache Iceberg works. And we've just added like a couple hands-on tutorials with using Spark and Dremio and whatnot. So you can see how Iceberg works hands-on a couple different angles. And then you can always follow me on Twitter at AMDA Lakehouse. I'm always posting a little like quick 1 minute, 2 minute videos showing different like examples and different features and cool stuff, so that way you can kind of see it in action. But with that, that concludes my story for today. And now that begins me answering your questions.
Thank you so much, Alex. That was a really great talk. We're a little bit over, so if folks need to go to other talks, there's event streaming is on right now. Feel free. I do have a couple questions for you if you've got a minute.
Oh yeah, I
Um,
got.
I'll kick it out while folks, if you want to ask questions, feel free to put them into the Q&A box. Yeah, so quick question. The merges. So, you create this structure of files. Is there something in the background that then collapses them so that the structure becomes more efficient over time?
When you say like the merges, we're talking about like compaction, where when we're
Yeah,
combining the
compaction. So for
files.
example, yeah, because let's say you put in like inserted things one row at a time, just to take a pathological
Mhm.
example, you just have you'd have millions of little teeny
Files.
files. Is there something that does data compaction automatically?
At the moment, right now, you would have to schedule your own jobs. Like the procedure is there, so it's like built into the library.
Mhm.
So you'd have to kind of create your own service currently. There are a couple services, like there are a couple solutions that are coming out. I know Dremio will have something that'll kind of do that. I think Tabular is also going to kind of eventually come out with something that does that. I think that's kind of in the roadmap.
Mhm.
I but at this very moment, there's nothing that's sort of
Okay.
currently out there that runs up current service.
And then a follow-on question. There doesn't appear to be any notion of a delete in this system. Is that correct? Other than just
I
removing the files completely. But if I wanted to do a delete and remove some number of rows, is that
oh
is
you
that supported?
now do you mean like a hard deletion of the in files, or do you mean just like running a delete query?
Just running a delete query.
Oh,
Yes.
you can do that. No, delete query is just fine. Like you can just run it like any other query, and it will either, if it's a copy on write table, just rewrite those data
Ah,
files
okay,
minus those
great,
records.
great.
Or if it's a merge on read, it'll do some other stuff.
Okay, great. I might have missed that on the well, paying attention to other things, but sorry if that's a question you already covered.
Oh, no, no, no. I didn't do a delete example, so understood.
Yeah, yeah. It's a difficult problem in these systems. Yeah. So if anybody else has questions, feel free to throw them out there. This was just a really fun talk.
Okay, I see
Really
one
good, really good
question.
description.
See one question in the chat. How does Dremio's
Ah, here we go.
product differ
Yes.
from Apache
Yeah.
Iceberg? Okay, so basically Apache, there's not, I wouldn't say like Apache Iceberg is a format, and basically any engine. So whether we're talking about like this year has been a huge year for Apache Iceberg as far as like people announcing compatibility. Like Dremio's been uh able to read Apache Iceberg for quite a while now. But I mean, throughout the year, we've heard from like Cloudera, from Snowflake, from Presto. Everybody and their mother wants to query Iceberg tables this year. But what Apache Iceberg offers all engines is going to be that improved query performance when it comes to planning the query. Now, Dremio is one query engine that you can use, and Dremio offers other angles of enhancement of the performance of your query. So in the sense that basically Apache, you have the Apache Arrow level, which basically if everyone's familiar with like DuckDB is super fast. One of the reasons is because of Apache Arrow and these kind of standard formats. So you have that angle. There's something called the columnar cloud cache that really allows to boost performance on cloud storage. Um, there's different techniques used for like Hadoop clusters, and then three, there's something called data reflections that Dremio uses. That is like the secret sauce that allows you essentially to kind of create materializations without the issues you usually have with materialization. So usually, like you materialize a table, you make this copy, but now you have to like everyone needs to know the query, the copy, and then on top of it, you have that like double. You just now create an extra like level of storage with like data reflections. One, you don't have to like query some other table. You just query the same table you have, and what it does, it creates like little pieces that can be reused. So if you were to materialize other views based on the same source data, it can reuse the same data reflections so that way you get the best bang storage wise and speed wise out of your materializations, which is super cool. But basically, you get that and you get the benefits of Apache Iceberg through from the metadata. And Dremio is really built with Iceberg in mind. So it works really well to really optimize the speed and performance of your queries on your data lake. So it's more like they complement each other really well.
Cool. You've got one. You got a follow on in the Q&A box from Kanti.
Oh, let me take a look. Let me open up the Q&A box. Oh, here we go. Okay. Would Dremio then be similar to Presto? Does it have any benefits compared to Presto for querying Iceberg? Yes, I would say like, but usually that would probably be one of the choices you'd be making. You'd be making, hey, should I use Dremio or Presto? I can speak more to the Dremio product, but like when it comes to Iceberg, I'm pretty sure Dremio has the widest selection of catalogs that it supports. So not only does it support Hive and it supports AWS Glue, which some, not all of the different options support, but it also supports Project Nessie at the moment. And then is growing support for Project Nessie with other engines. But I mean, Dremio goes so far that it actually provides Nessie as a service. This is a service that's currently in preview, public preview, called Dremio Arctic. And what it is, it's basically Nessie as a service. So you get that. You don't even have to like set anything up, set up the service. You literally just click, I want an Arctic catalog in your Dremio account, and you now have this catalog with Git-like semantics, and you actually have a visual UI where you can create those branches and merge those branches with your Iceberg tables. So it makes it really easy to work with. I would say it makes it really easy to work with Iceberg. Actually, recently on Twitter, I posted several videos where I was actually showing off a lot of the different Dremio features with Iceberg. So definitely follow me on Twitter and check out those recently posted videos. They are pretty cool. I show a lot of cool things like doing multi-table transactions and how easy it is to like take a JSON file and turn it into an Iceberg table and things like that.
Hey, great. Alex, we're gonna have to give you a longer time slot next time so you can. The subject is really deep. I don't see any further questions. So at this point, thanks again, Alex. It's been super informative, and I really appreciate it. Look forward to more of your talks.
No problem, no problem. Always, again, follow me on Twitter. I'm always, I'll be. I think my next appearance will be at Data Day Texas, in January. So but yeah, I thank you very much for having me.
Yeah. Thanks, everybody. We'll call it a day and on to the next talks. Talk to you soon. Bye.
Talk to you soon.